Okay, so before I begin today's content, you guys took the midterm last week. The grades have been posted. You should be able to see how you did. If you'd like to review your actual exam, see what questions you got wrong, you're more than welcome to do so. Just send me an email so I can pull your exam out of the stack and bring it to class. That way I don't have to carry the whole stack each week. So just send me an email. I'll bring it and you can take a look. There's always questions about what the final is going to look like. So the final will be, mostly stuff from here on out. So chapters 7, 8, and 9 will cover about 80% of what's on the final. The remaining 20% will be stuff from before, in chapters 1 through 6. It's and that will be kind of more conceptual, definition-based questions for chapters 1 through 6. But most of the final will be stuff from chapters 7, 8, and 9. And I will have a practice final, or I think I already do have a practice final posted online for that. Okay. So today we'll get into chapter 7. Which is all about sampling, and sampling distributions. Okay. So I'd like to kind of just take a broad, big picture look at kind of the course and where all of this fits in and what you've learned so far, how that fits in. So we've talked about, we said, the point of statistics is that statistics allows us to make conclusions based on limited data, or make conclusions about the population based on a sample of data. Okay, and the idea being that the population is this large entity that is too big for us to observe directly. So what we have to do is we take just a tiny little sample out of it, okay, and we observe the sample. And based on what we see in the sample, we then go back and make conclusions about the population. Okay, and this process is called statistical inference. Okay, and generally the population has a property which we call a parameter. Okay, so the population has a property that we're interested in. Okay, and so this is called the parameter. Okay, so for example, we can ask, what is the average weight of, I don't know, of a tiger. Okay, so the average weight of all tigers in the population would be the parameter. Okay, so the parameter would be average weight of all tigers in the population. Okay. And again, we can't, the population is too big or too difficult for us to observe directly, so we have to observe a sample instead. Okay? And so the corresponding value in a sample is called a statistic. So in this case, in our example, the statistic would be the average weight of the tigers in a selected sample. All right. Is that okay? Hold on, sure. Okay, and so, depending on the scenario, we could have, for categorical variables, so, you could have the population parameter would be, it could be the proportion in the population with a certain trait. Okay, and the symbol there would be P. Okay, and we would just call this the population proportion. Well, in this case, the P represents population proportion. Okay, we use the letter P a lot in the course, and they take on different meanings depending on the situation. Okay, and I'm sorry. That's just how the.
We were saying probability with PR before. So
Yeah, a lot of times, but yeah. So we've got P, and this is the population proportion. The corresponding sample statistic would be the proportion in the sample. With the trait. Okay, and the symbol to distinguish it from the population proportion, we call it P hat. Okay, and this would be the sample proportion. Okay, and don't get P and P hat mixed up. P hat represents the, in this case, the sample proportion. And over here, the P is the population proportion. Okay. And this applies for categorical variables, because we're dealing with proportions, right? All right. If we're dealing with numeric variables, then we'll have the population mean, and the symbol for that is this, mu. Okay. And the corresponding sample statistic would be the sample mean.
I guess mu hat.
No? What's the symbol for the sample mean? It's X bar. Some textbooks do write mu hat, but I'd say that's much less common. Okay. Then you have the population standard deviation. And the symbol is sigma. And corresponding, we have the sample standard deviation. And the symbol for the sample standard deviation is S. Okay?
And these are for numeric, right?
And these are for numeric variables. Okay. And so, oftentimes we want to make conclusions about one of these population values, and to help us with that, we have to look at their corresponding sample statistic. Okay. All right, so let's just have some general ideas about sampling. Okay, and so if we want our conclusions about the population to be valid, our sample needs to be representative of the population. Okay, and it's actually quite challenging to get a representative sample. Okay, and so you know, if our sample is not representative, okay, it is said to be biased. And as far as bias goes, okay, there are many reasons for why a sample could be biased. Okay. Okay, and you can read, page 311 in the text. There's non-response bias, or there's sampling bias, et cetera, et cetera, et cetera. So, if you were to survey people about their political opinions or things like that, depending on the way you phrase the question, that can skew your results. Depending on when you conduct your survey. If you call people's houses in the middle of the day, that's going to skew your results because you're less likely to get people who are working in the middle of the day and things like that. We have a question.
Yeah, as far as the first point, you wrote that this is a difficult task.
Mm-hmm.
I remember in the first or the second one, you said something about that the random machine.
Simple random sampling?
Yeah, so why is that difficult?
So I was gonna, I'll talk about simple random sampling and just even the difficulties in the kind of the quote simple method. Yeah, but yeah, there's anyway, going on about bias, there's lots of reasons why things can be biased. If you call people, they might just say, I'm not interested in answering questions. And then you might get people who are eager to participate in your survey and things like that. And so whether someone is willing or unwilling to participate may be linked to the types of answers you get, okay? So, if you were to call someone and you say, do you have a few minutes, can I ask you for a few minutes on your opinions on, I don't know, gun control or something like that, right? And then, so some people might just say, no, I'm not interested in answering questions. And some people might say, oh yes, I have time. And so the people who do have time to answer the questions may or may not be reflective of the entire population. And so your answers from these surveys could end up being biased in that it doesn't represent everyone's opinion, okay? Maybe. So one method that should give representative samples. Okay, but is not guaranteed to. Okay, so it should, but is not guaranteed to give representative samples is simple random sampling. Or we might call this SRS. Okay, and so with in simple random sampling, okay, all individuals in the population have an equal chance of being selected. Okay, and all possible samples and all possible samples have an equal chance of selection. So, and what we mean by all possible samples, you can kind of think of lottery numbers. So if you play Powerball or whatever it is, you know, they draw, I don't know, 6 numbers, 7 numbers or something, and every single number has an equal chance of being selected, and every possible combination of numbers has an equal chance of being selected. So the combination, you know, 12, 15, 26, 33, 42, and 55 has the exact same probability as the combination 9, 12, 58, I don't know, 41, 39, and something else, okay? Like every possible combination of numbers has the same chance of being selected, okay? And that's because the way lotto numbers are selected is via simple random sampling, okay? To do simple random sampling requires a sampling frame. Okay, and a sampling frame is ideally a list of everyone in the population. Now this is the hard part in simple random sampling, is getting the sampling frame. If I said, do a simple random sample of the people in Los Angeles, you would first need a sampling frame, which would be a list of everyone in Los Angeles. And this is a nearly impossible task to do, okay? There's no, you know, when you come to LA, there's no single agency that lists, you know, monitors who comes in and out of the city, okay? Now there are, you know, different databases. There's like the DMV and registered voters and things like that, but that's not a list of everyone, okay? You're not gonna have, you know, people who don't have permanent addresses, or, you know, people who aren't registered or whatever. They're not gonna appear in these lists. So, you know, whatever deficiencies exist in the sampling frame, those same deficiencies will exist in your random sample. Okay, so I mean, if you this would be very silly way to answer this question, but you could say like, oh, I wonder what percentage of people in Los Angeles are homeless, right? And then you say, okay, I know what I'm going to do. I'm going to go to the DMV and get a list of everyone in their system who has a Los Angeles address. And then you'd say, oh, well, I selected 1,000 people, and all 1,000 people, none of them were homeless. Therefore, I conclude that 0% of people in Los Angeles are homeless, okay? Obviously, we can see the problem in trying to answer a question like that by using a flawed sampling frame, right? So, if you want to get a survey of like, what percentage of drivers, I don't know, have gotten speeding tickets or something like that, sure, the DMV would be an appropriate place to start, okay? But if you're trying to ask other questions that may or may not be linked to, whether someone has a permanent address or not, how you select your sampling frame is going to have problems, okay? Or could cause some problems, okay? So a list of everyone in the population. So the difficult part is getting a true sampling frame, okay? But once you have your sampling frame, then simple random sampling is easy. Just use a random device, maybe a computer that gives you random numbers. Use a random device and select people from the sampling frame one by one at random. Okay, and the sampling frame is a list, and so you go down the list, and then you use the random device to select things at random, and then you pick. Okay, at random means truly at random, using some kind of random device. You can't just close your eyes and stab the paper and say this is the person I select, because when you do that. You can create like a heat map of areas on the paper that are more likely to be touched than other areas, and people are just very bad at being truly random. Okay, and sometimes and there's some scenarios where you think you don't need a sampling frame, but you really do. So, for example, let's say we were working in some laboratory and we had mice in a cage. Okay. And I said, I want to select some random mice from the cage. I'm going to just reach in there and I'm going to grab a mouse, and this will be my mouse that I select. Now, if I reach in there and I grab, let's say I'm going to grab 3 mice. I'm going to just reach in there, close my eyes, and grab a mouse. Is this going to result in a random sample? Okay. Why would this method not result in a random sample? Yeah.
No, because you'd subconsciously reach for the one that doesn't bite.
Maybe the one that doesn't bite, but what? I think
the ones, for example, in the top corner don't have the same chance of getting picked compared to the ones right in front of you.
Yeah, or I was just going to say you're more likely to end up getting slow mice that aren't going to run away. Mice, there's all sorts of reasons why it's not going to end up random. Yeah, mice that hide in the corners maybe are unlikely to be selected, or mice that aren't afraid of your hand, or mice that just are slow, those are more likely to be selected. So if you wanted a truly random sample, first you'd have to select all the mice and label them, put little tags on them, 1 through 20 or whatever it is, however many you have. So you number them 1 through 20. Then from that list of 1 through 20, you select 3 random numbers using a computer or some kind of random device. And then once it says you need to select mouse 6, mouse 7, and mouse 15, then you go back into the cage and select those 3 mice. That's how you can get a random sample. But if you just reach in there and grab 3 mice, that's not going to work. Yeah?
Are there a set of rules for the
the rule is use a random device to kind of generate to pick from the list who you're going to select, okay? So basically, first you need a list of everyone in the population, okay? If you got 20 mice in a cage, it's very easy. You just number them 1 through 20, okay? I mean, it might be a lot of work labeling them 1 through 20, but you can get a list. That's your sampling frame. And then you use some kind of like a random computer or random digits or something to select numbers from that list that way. So, but yeah, the hard part if it's a big population is getting that sampling frame, the list of everyone. That's difficult unless you're dealing with, you know, a single organization like a school or something like that. Okay, so let's talk about what a sampling distribution is. Okay, so let's say we've selected a sample at random. We've got a simple random sample. We can now talk about a sampling distribution. A sampling distribution is the distribution of all possible sample statistics from random samples taken from a population. Okay, now this may not make a whole lot of sense at this point, and that's okay. I'm going to try to illustrate how we generate a sampling distribution. Okay, so we're going to do the sampling distribution of p hat. This will be our example. Okay, the sampling distribution of p hat. What is p hat?
The sample population.
The sample proportion, okay?
Yes.
So the sampling distribution of our sample proportion. Okay? And so the sampling distribution of p hat would be the distribution of all possible p hat values that arise from random samples from a population. Okay, so let me illustrate that. Okay, so let's say we've got this, let's say we've got a big tank, all right? And in this tank, we've got a bunch of candy, okay? And we're gonna fill it with Reese's Pieces candies, okay? So we'll say this thing is full of hundreds of pounds of candy, okay? Hundreds of pounds Reese's Pieces candy, okay? So if you don't know, Reese's Pieces are like, they look like M&Ms, but they've got peanut butter inside, okay? And they have three colors. They can be orange, yellow, or brown, okay? Okay, let's say that somehow, you know, we've counted all of the pieces, and somehow we know that in the tank, that exactly 30% of the candy pieces are orange. So to say that this is the population proportion is 30%, okay? So this is, of candy pieces are orange. This is in the population, right? We're going to say P is equal to 0.3. All right? So we've got this machine. It's full of hundreds of pounds of candy. Exactly 30% of these candies are orange. Okay, so if there's 10,000 pieces of candy in here, then exactly 3,000 pieces are orange, or something like that. Or if there's 100,000 pieces, then exactly 30,000 pieces are orange. Okay, so and it's all mixed up here. Okay, I'm going to go in there and I'm going to take a scoop, and I'm going to pull out 50 pieces of candy. Okay, it's going to be a random scoop of candy. Yes.
So you're going to do 2 samples? Because what I understood, this whole pounds of candy are already sampled, no?
This is going to represent our population. Okay, so we're gonna say this is going to represent a population of candy. Okay, so this will be our population. Okay.
And now we're going to take a sample.
And now I take a scoop. Okay, I take a scoop of candy out. Okay, and I'm going to get n equal to 50 pieces of candy. 50 pieces of candy. This is a random sample. Okay, so when I dump out the pieces of candy and I count them, how many are going to be orange? It's a random sample. Okay, well, the answer is because it's random, we don't know. Okay, we expect about 30% of my sample to be orange. Okay, so we're expecting around 15 pieces to be orange. But because it's random, I could get more than that. I could get 18 pieces that are orange. Or I might only get 12 pieces that are orange. Or I could get 10 pieces that are orange, or 16 pieces that are orange, right? So, we're expecting we would expect about 30% orange candies. Okay, so let's, we count them, and let's say we count, we'll say 18 orange pieces. Okay, so my p hat for this sample is going to be x over n, 18 divided by 50, 0.36. Okay, so in this random sample, I got p hat to be 0.36. All right, we're going to dump those candies back in, put those back into the thing. We're going to stir it up. We take another random sample. Okay, another random sample, n equal to 50, and then this time x is equal, let's say, 14. Okay, we get 14 orange pieces. Okay, so this time my p hat is 14 over 50. I get p hat equal to 0.28. Right, and I'm going to just keep doing this over and over and over again. I'm going to keep track of all the different p hats. Okay, so
Wait, you said you wrote 15 over 50 instead of 14 over 50.
I'm sorry, I meant to write 14. Okay, 14 over 50, I get 0.28. So we take another sample. Maybe my p hat is 15 over 50. Okay, and so my p hat in this case is 0.3. Okay, and we do this again. Another sample, and for every sample, we're going to record a new p hat. Maybe I get p hat is 19 over 50, and I get 0.38. Okay, another sample, and we just do this again and again. Okay, yeah. So what we're going to do is we're going to do this over and over and over again. And we're going to keep track of all the different p hats that we get. Okay? And then we can create, when we keep track of all the different p hats, we get a distribution of p hats. We can see which p hats are more likely to occur, which p hats are less likely to occur. Okay? Okay, and we get a distribution. Okay, and then we can say, you know, we can see which p hat values are likely and which ones are unlikely. It's okay? All right. So I'll let you guys get that written down.
Are we basically going to compare which p hat, or are we also going to compare, or are we also going to compare p hats that are above the?
Yeah, so well, here, first of all, we want to create our sampling distribution. Oops. Give me a second here. So I'm going to do, okay. So this is kind of the demo. All right, so here I'm going to just, we're going to draw 50 pieces of candy out of this machine, and exactly 30% of these candies are orange, okay? So I'm going to run the simulation, all right? And you can count how many orange pieces I get, okay? And so here, if we count them, we have a total of 14 orange pieces, okay? 14 divided by 50 is 0.28, so my sample proportion is 28%, okay? And then to keep track of it, I'm going to create a dot plot down here. So I put p hat, I put a dot at 28%. Is that okay? And then just to speed it up, I'll do this, okay? So in this case, we got 18 orange pieces, okay? And my p hat is 0.36. I'm going to put a dot here at 0.36. Okay, we'll do this again. This time I only got 9 orange pieces, so my p hat is 18, okay? So, you know, every time we're taking a scoop of 50 pieces of candy out, and we're going to count how many orange pieces we get, okay? And, you know, sometimes we get more, sometimes we get less, okay? And then here I got, what is this? 10 orange pieces, so that's 20% orange, and we get a dot right there at 0.2. And we just keep doing this. Here I got 15 orange pieces, 30% orange, okay? And we can speed this up. I mean, we can keep doing this one at a time, and then just, you know, getting a new dot, 20%, another one, and then here's another one, 26%, and we just keep doing this, okay? Now I can kind of, so this is after 10 trials. This is what we got. We'll do this, you know, I'm doing this 10 at a time now. So every time I hit the button, 10 more dots appear in our thing. So at this point, I've taken 50 samples of 50 candies, and every time I've counted how many pieces of orange, how many are orange, and I'm creating a dot plot. Yeah, there's one, you know, one time I got 48% orange, okay? All right, this is after 100. All right, and this is we're starting to see a kind of a pattern emerge. after, so this is after 300 samples, okay? We can see at this point the dots are getting so close together they're almost going to form vertical lines. But we can see that certain values like 28%, 30%, 32%, these values are appear quite frequently, all right? Values out here, you know, 46, 48%, they've happened, but less frequently, okay? Values as low as 12 and or looks like 14 and 16% have also happened, but very, very rarely, okay? So I'm gonna just crank this up and we'll do like another, here's 700, this is after 1,000 simulations, okay? After 2,000 simulations, after, okay, so here it is after 10,000 simulations, okay? So we've done this simulation 10,000 times now, right? And we see kind of, you know, the lines are starting to smooth out a little bit more, and we can see truly that these proportions here in the middle appear most frequently, the middle being around 30%, okay, which makes sense, right? If in the tank, we know the tank is exactly 30% orange, whenever we take a random scoop, we would expect something around 30% to be orange. But because it's random, it might be a little bit higher than that, it might be a little bit lower than that, okay? And so yeah, values close to 30%, like 28 and 32 and 26% or even 34%, those are quite likely to appear, okay? Values that are a little bit more extreme, like 44%, 46 and 48% do happen, but very rarely, okay? And on the other side, values that are extremely low, yeah, do happen, but are also quite rare. I mean, because it's a random sample, is it possible that only 10% of the candies are orange? Like if I scoop out 50 pieces of candy, it is possible that I get only 5 orange pieces. That is possible, okay? But it's unlikely to happen, okay? And we can see that indeed it did happen, but very, very, very rarely. Yeah.
So with SRS, do you always end up tending towards standard normal, or not necessarily?
Yes, so this is this phenomenon. So what this looks like is it looks a lot like the normal distribution, right? So we can actually overlay the normal distribution on top of it, and we see that it looks almost exactly like the normal distribution. And this is kind of this mathematical phenomenon, and it's defined under you know, this property called the central limit theorem. Okay, and we'll talk about all of this. But I just kind of wanted to demonstrate the idea of a sampling distribution. It's the idea of we're going to repeatedly draw from the population, okay? And every time we draw from the population, we record the p-hat value, okay? And we do this over and over and over and over again. And if we keep track of all the different p-hat values, we see certain p-hat values are more likely and other p-hat values are less likely to appear. Okay? All right, and so what we see is that this thing ends up looking a lot like the normal distribution. All right, I'll put this into our notes. All right, is this okay? Are there any questions on what we see here? Okay. Huh?
Sort of like the law of large numbers.
So the law of large numbers basically states that the more times you do something, it approaches the theoretic distribution or the theoretic probabilities. And so the law of large numbers plays into the fact that I did this 10,000 times. After only doing it 1 or 2 times, sure, we might have gotten 40% orange in one case or 12% orange in another case. But after doing this 10,000 times, then the true patterns emerge, seeing that 30%, 32%, 28%, those are much more likely the other ones. Yeah.
So basically what you're saying is that if you go to Las Vegas, if it goes well to you, stop.
Exactly. Yeah.
Stop and leave.
Yeah, because all the games in Vegas are designed to favor the casino, and so in the long run, so that yeah, if you are lucky in the short run, you should stop because, and you know, the longer you play, you are more likely to lose in the long run. Okay, I mean your lucky streak could continue. That's certainly possible. Okay, but okay. So anyway, what we see is that. So this is the sampling distribution of p hat. Okay, it shows that values of p hat close to 0.3 are more likely to appear. Okay, and values of p hat that are, you know, much higher than 0.3 or much lower than 0.3. Okay. While possible, are less likely to appear. And the overall shape looks very much like the normal distribution.
Question.
Yes.
Is there a higher chance for the drawing to be more than 0.3 or less than 0.3?
Well, because we're going to say that it looks very much like the normal distribution, we're going to say it's equal. That if 0.3 is in the middle, the normal distribution is, you know, it's symmetric, so you have...
Is it symmetric?
So the truth is no, it's not perfectly symmetric, okay? But it's pretty close to symmetric, okay? But if you looked at all of the actual values and everything, it's not perfectly symmetric, okay? But it's pretty close to symmetric. And so we don't have to deal with all of the complications of everything. We're going to just kind of say it is symmetric, and we're actually going to approximate things with the normal distribution, assuming all of the properties of the normal distribution, okay? So getting this exact distribution, it's possible, but the math is rather complicated, and we don't want to trouble ourselves with it. So what we're going to say is that this shape, the sampling distribution itself, we're going to approximate the sampling distribution with the normal distribution. And that's going to make our life a lot easier, because we know how to deal with the normal distribution, okay? Or at least we should at this point. So we know how to deal with the normal distribution, so we're going to just use that as an approximation, okay? The true distribution is a little bit more complicated, but it looks very much like the normal distribution, and so we're going to just pretend that it's like the normal distribution and go from there. Okay? All right. Is this okay? So we're going to say, I'm going to copy this part. All right, so we'll say the sampling distribution of p hat can be approximated with the normal distribution. Okay? All right, and so there's something called the central limit theorem. It's kind of the mathematical proof showing that the sampling distribution of p hat is similar. So I know in the picture we're saying it looks similar. There's an actual mathematical proof that says not just the picture, but really mathematically we can prove that it is. Okay? Distribution under certain conditions. Okay? And so all normal distributions have a mean and standard deviation, okay? And so what we're going to say is that the normal distribution that approximates the sampling distribution has mean equal to p and standard deviation equal to the square root of p times 1 minus p divided by n inside a square root. All right. Is this okay? All right, so let's put this together and let's try something out. Okay, so we'll say, let me kind of throw this here. All right. So we're gonna just say, you know, here's our tank of Reese's Pieces. Okay. Okay, so we got, you know, we have a tank of Reese's Pieces candies in the tank. 30% are orange. Okay, and we take a random sample of 50 pieces of candy. Okay. So, if I take a random sample of candy, could I get just 20% orange pieces?
Yeah.
Yeah, okay. That means I only got 10 orange pieces in my sample, okay? So, is it possible to only get 20% orange candies? Percent orange candies in the sample? And the answer is yes, okay? And so my question is, what is the probability that a random sample of 50 candies ends up being only 20%, ends up having only 20% orange or less? Okay, what's the probability that this random sample ends up being 20% orange or less? Okay, and so our sampling distribution, keep in mind the sampling distribution can be approximated with the normal distribution. Okay, the mean is p, and the standard deviation is p times 1 minus p over n inside the square root. Okay, so this is everything you need to answer this question. All right, see if you can kind of put the things together to answer it. We'll go over the answer in a little bit. I'm going to pause the video if you're watching on YouTube. So I advise you to pause also and try working through this problem yourself. Okay, well, let's take a look. So what we have is we've got this normal, so we have a sampling distribution, okay? And the sampling distribution is actually kind of this complicated thing, but we're going to just make our lives easier and say the sampling distribution is going to be approximated with the normal distribution. And it's okay to do that, okay? It's like, you know, is the Earth a perfect sphere? No, it's not. Can we pretend that it is? Sure, we can, okay? So for the purposes of our calculation, we're going to pretend that it's the normal distribution, okay? And so what we have is we've got this normal distribution, okay? And the mean of this normal distribution is p, okay? What's p? It's our population proportion, and what is the value of p in our problem? 30%, because in the tank, 30% are orange. So in our population, 30% are orange, 0.3 are orange. So our p is 0.3. Okay, what's our, and this is going to be our mean. Okay, so that means in the middle of our picture, we put 0.3. And we want to know what's the probability that we're going to get 0.2 or less. We want to know what's the probability that I'm getting 0.2 or less. Okay? 0.2 or less. So yeah, what's the probability that a random sample of 50 candies ends up having only 20% orange or less? Okay? So to figure that out, we need to figure out our standard deviation, which is going to be the square root of p times 1 minus p over n. So I'm going to put in 0.3 times 1 minus 0.3, or that's going to be 0.7, divided by 50, okay? And I want to get the square root of that. So I'm going to do, we'll do square root 0.3 times 1 minus 0.3, and down below I put in 50, okay? 0.3 times 1 minus 0.3 divided by n. And I get 0.064807. 0.064807. All right. Okay. I actually don't even have to write the whole thing out here because what I want to do is I want to get the z-score. Okay. I want to get the z-score for 0.2. So I want to know what's the probability of getting 0.2. Because this is now a normal distribution problem, I just want to know what's the area down here below 0.2. So I'm going to find z is equal, and what would I plug in for my z? 0.2 minus 0.3, it's always our x minus the mean, divided by our standard deviation, which is 0.064807. Okay? So what I'm going to do here is I'm going to do 0.2 minus 0.3, okay? And then the last number I calculated was 0.064807, so I'm going to just hit divide by the answer button, okay? Or I could type out the whole number, but I'm going to just do 0.2 minus 0.3 divided by the answer key. And I get negative 1.543. When you're dealing with z-scores, you got to round off to 2 decimal places. So I'm going to just say z is equal to negative 1.54. Is that okay? All right, what do I do now? We have a question.
Where do you put the 0.2 minus 0.3 then?
Because the question said, is it possible that only 20% of the candies are orange? And so that's going to be 0.2. The mean is the number in the middle, which is our population proportion 0.3. Okay? So I want to know what's the area over here, so I'm going to do 0.2 minus 0.3. We're getting the distance from the mean, and we want it in standard deviations. So this value is 1.54 standard deviations below the mean. Okay, what do I do once I have this number?
You plug it into the table.
We go to the z table, right? So we go to the z table, and I'm going to look up negative 1.54, 0.0618. Okay, so the area to the left of negative 1.54 is 0.0618. Okay, so what does that mean? It means if in the tank is exactly 30% orange, right? When I take a random scoop of 50 pieces of candy, is it possible that only 20% of them end up being orange? Yeah, it's possible, okay? How often does that happen? It happens only about 6% of the time. Okay, so it doesn't happen that often, but it does happen, okay? Most of the time you'd probably get more than 20% orange, but by random chance you might get less than that. So the answer here is 0.0618. Okay, and again, this is an approximate answer, but for our purposes, it's good enough. Okay, let's try another example, and then we'll take a break. Okay. Was this problem okay? All right, we'll give you another example. Let you try it out. Okay, so let's say in the population, we'll say 15% of people are left-handed. Okay. Let's say we take a random sample we'll do 100 people. Okay, we take a random sample of 100 people, and we want to know what is the probability that your random sample has over 20% of the people 20% of the people being left-handed. Or maybe I'll say 20% or more of the people being left-handed. Okay. Okay, so go ahead and try this out. Okay. Let's take a look. For the answer, are we getting something around 0.0808?
Yes.
Okay. So if you got that, then you're in good shape. All right, let's start off by drawing a little picture here. Okay. All right, and so what we have, let's figure out what our P is, because that's going to go in the middle. So what is our population proportion?
0.15.
0.15, right? So here we're saying 0.15 goes in the middle, meaning whenever I take a random sample of people, I would expect around 15% of those people to be left-handed. Maybe I get a few more than that, maybe I get something less than that, but overall around 15% will be left-handed in our sample. And what we want to know is that what's the probability that I get 0.2 or more? So I want to know kind of what's this area over here. All right, so our standard deviation is going to be the square root of p times 1 minus p over n. So I'm going to put in 0.15 times 1 minus 0.15 divided by 100. So clear that. 0.15 times parentheses 1 minus 0.15. Let's close that parentheses. Divided by 100, okay? And I get 0.035707, okay? So that's my standard deviation. So my z-score, looking at this picture, is going to be 0.2 minus 0.15 divided by my standard deviation, 0.035707, okay? So again, I have that punched in already here, so I'm not going to bother retyping it. I'm going to use the answer key. So I'm going to just do parentheses 0.2 minus 0.15, close my parentheses, and divide by the answer button. Okay, I'm going to hit equals, and I get 1.40028. Okay, so I get a z-score of 1.40, rounding off to 2 decimal places. Okay, so at 1.40, I look that up in the z-table, and at 1.40 I have 0.9192. Okay, so the area to the left so that's going to be this area over here. This area over here is 0.9192, meaning this area over here is 1 minus 0.9192. Okay, because I'm asking what's the probability that we have 20% or more. So I'm going to do 1 minus 0.9192, and I get 0.0808, and that's going to be my answer. Okay. So if you take a random sample of 100 people, you expect about 15% of those people to be left-handed. Is it possible that you get more than that you get 20% left-handed? Sure, that's possible. How often does that happen? Happens with a probability of about 8%. Okay, happens about 8% of the time, yeah.
So over here, you're pretty much asking us what's the probability of like more than 20% will be left in.
Mm-hmm.
How can you check what is the probability of 20% exactly?
Okay, yeah, 20% exactly cannot be done with the techniques we've learned in this class, okay? It can be done in another statistics class, but not in this one, okay? So not in the intro class. Okay. All right, why don't we take a break here, and then we'll continue on.